So we will dive deeper into how to implement SSD. So Euler is very similar, but the fast RCM family is very different. It's pretty complex. So it's hard to explain in 20 minutes. So we're gonna just explain SSD. Okay. The first one is how to do category prediction. So here, assume we have number of anchors, like given a feature map, we have given the input is number of anchor boxes, and then give the number of classes. So for each anchor box, we will predict number of class plus one category. The plus one means the background. It means don't belongs to any class. So what do we do here? We do a convolutional kernel. The output channel will be the number of anchors times the number of class plus one. Okay, so this is because for each anchor box, we need to generate number of classes plus one prediction. It's a class prediction. Okay, and then why we choose convolutional 2D is because we choose kernel size equal to 3, padding equals to 1. Then we know that the output shape will be the same as the input shape, which means every pixel in the feature map, we're going to have a coding pixel in the output. In addition, for each output, we have number of anchors times number of class plus one channels. So that is each output will predict the anchor boxes centered at that pixel. And because we have a number of anchor boxes and so many classes, we need so many channels. Okay, that's the little bit different to what we had before. Before we only need to predict the whole image. So the output channel, what we did like net in net, is that we do average pooling, so make into a single feature map, and the number of channels equals the number of class. But here, we don't do average pooling because we need to predict for every pixel. Okay, any questions here? Okay, so that is the concept change, how you to predict so many different kinds of outputs. Similar thing for bond, okay, let's do a sanity check. So we have a function called forward. Given input x, given network, we first initialize it, and given x, I just return the output. So if the input is like 2 by 8 by 20 by 20, 2 is the batch size. 8 is the number of channels, the input channel. 20 by 20 is the feature map, with the width and height. And if I'm going to predict a number of 5 anchor boxes and 10 classes, then the output should be the batch size we don't change. And this is the feature map height, feature map width we don't change. We only change the output channel. The 55 equals to number of anchors times 10 plus 1. Okay, so all these things are predictions. Given each example, we're going to generate so many predictions here. Any questions? Good. Similar thing for the other thing, we can generate, like, no matter what the input channel we have, then we always generate 3 times 11 is 33, and 10 by 10, this is the input feature map. Okay. Another thing is that we want concat all the prediction for multi-scales, because we output for each scale, every scale have different feature map. We want to concat them together and fit into loss function. So what we do here, we transpose the number of output channels into last layer, into last channel, into last shape dimension. And then this is the height, this is the width. And then we flatten, which means we transpose into 2D matrix. And then we concat for different scale. We're going to concat then on the first dimension, which is not the batch size dimension. So the goal here, the Y1, we can think, if we assume Y1, this is the first scale, Y2, we half of the width and the height, and we want to concat together. That is, we make it into a matrix and put the number of channels, which is the channel, is the kinds of the number of classes we have into last channel, and do flat into 2D matrix. And then at the end, you give a 2D matrix. The column, number of columns is pretty high. Okay, that's a way how we can put the output for different scale together. Similarly, how to do bounding box prediction. We know that the bounding box is just the 4 numbers. So we only need to know number of anchors, and then the output channel will be, for each anchor box, we're going to predict 4 values. This is the anchor box. We can define the anchor box. And then similarly, we have kernel size equal to 3, padding equal to 1, so that we generate the same output as the input. Okay, so now we know how to do prediction layers. And the other one, we mentioned that we have downsample box, that is half the height and the width. So it's pretty easy here. Well, you can see that, assume this is the number of the channels of the input. What do we do here? We add in 2 blocks. The first one is conv 2D, kernel equals to 3, padding equals to 1. Basically, we don't change the number of channels is output channel, it's not the input channel. We don't care about the input channel. So firstly, we use a conv 2D map to the output channels. We didn't change the height and the width here. And adding as normal as we have a ResNet before, we add in batch long here. And after batch long, we do a ReLU. This is the typical block we have in ResNet. Then we add in 2 such blocks to get how to do feature instructions. And then last, we do max pooling. So strat equals to 2, then which means we can reduce the height and the width by half. Okay, so this is a downsample block. So for example, given an input, we have 20 by 20 and fit into the downsample block, and output channel is 10, then we don't change the number batch size, 2. We change the shape. We change the channels to 10. And then most importantly, we reduce 20 by 10. Okay, this is downsample block. Okay, the last one, we need a base network. Usually we pick up ResNet or any one we learned before. And also we can, for fine tuning, we can use a pre-trained network. But here, just because we're going to use a very simple data set, what do we do here? We just concat a bunch of downsample blocks together. Like, we first use a downsample block to 16 number of channels, and then reduce the height and the width, the height and the width, and but double the number of output channels, and double again. Basically 3 downsample channels as the base network. Okay, that's the for tiny case. So if given the input size, 2 batch, RGB 3 channels, 256. So this one just reduce the height and the width by 8, and also change the number of channels to 64. So that's the base network we have. So basically, we have implemented the base network, the downsample box block, and also the prediction for category and the classes already. So now we are ready kind of to get a block. Given the block, we have 5 blocks here. Still goes to here. Block 1 base network. And in the middle 3 is the downsample block. The last one, we actually just do, sorry. The first one is a base network. And for 1, 2, 3, we use a downsample block. The last one, we just do a global max pooling to reduce the shape, the features into one by one, no matter how large you have. Okay. So the network, we have 5 stages. So here's another thing. Given a block, how to run a forward function? So this is a little bit different to what we have for classification before. So assume the block is the model, and then we have how to choose the size, which means different size for the anchor box, which is a list. The ratio, the list of ratios we're going to choose for the anchor box. And the class predictor, the bounding box predictor. So first we do here, we feed into the input into a block to get a feature map, which is y. And then we know that we showed this function before, like given a different shape, different size, given different ratio, going to return a bunch of anchors. So for this block, given the input shape, given the list of size, the list of ratios, we will have the anchors for this block, the output of this block. So then we feed the output of y into the class prediction and feed the y into the bounding box prediction. Then the output, we have 4 things. So here's the feature map, y, which is going to be the input for the next block. And the anchors for this feature map, also the class prediction and the bounding box prediction for each pixel we have. Okay, so we have 4 output. And the previous classification, we only have a single one. But because now it's a little bit complicated, we have 4 here. Let's do a sanity check here. We're given different size because we have 5 stages. This is the output of the base network. And this is kind of the 3 downsample network. And this is for the last average pooling. And we choose different size. Well, it's pretty random number. You can see we start with 20% of, well, this is pretty random. So we start with 20%. The anchor box will be 20% of the original feature image. We cover 20% of the area. And the next level, we change to 0.37. Well, we basically just, what we do here, what we do here, we pick up the last one. The last layer, we cover large objects, cover 88% of the original input. And then we linearly find this 0.37, 0.94, like 0.37 minus 0.2 is equals to 0.17. Similarly, this is equal to 0.17 equals 0.54, and basically this is a linear scale between the first 0.2 and the last 0.88. Okay, so how about the second shape? The second shape actually is the square root of 0.2 times 0.37. It's kind of in the middle. Similarly, this is kind of the square root of this guy times this guy. Kind of sit between. Okay? So for the ratios, first we use a square ratio. Then we choose 2, which is one side is 2 times larger than the other side. And we choose another one, 0.5. And for each scale, we just choose the same ratio. So the idea here, for the bottom layers, we use kind of small anchor box, trying to catch up small boxes. For the last one, we use the larger ones here. Okay, so then for each scale, the number of anchors will be, this is 2, and plus 2, plus 3 minus 1, which is 4. For each pixel, we're going to generate the 4 anchor boxes. Okay, any question here? Okay. Then we have the whole model. We call it tiny SSD because it's not actually SSD, because the base network is pretty small. So we can a little bit complicate, but not too much. The thing here, to the initialization, we have the number of classes. And then we have 5 blocks. We use the Python set attribute where because we want to have a self block underscore 0 means get the first block kinds of, and so this is kind of the way we don't want to have a list. This only thing. For each block, we get the base block network, get a predictor, get a bounding box class predictor, bounding box predictor. So this is, we have 5 stages. We have actually 15 kinds of different blocks. Then in the for function, so firstly we have each block, each level, we're going to give you anchors, class prediction, bounding box prediction. Then what do we do here? For each stage, we feed X input and get the blocks, get the block, get the sizes, get the ratios, get the class predictor, get the bounding box predictor, fit into the blocks forward function we defined before, and we get X anchors, class prediction, and the bounding box prediction. At the end, at the end, we do here, we just concat all this output for each layers together. So at the end, we concat all the things. We concat the anchors. We concat the class predictions, also the bounding box predictions. So here, the reshape means for class prediction, we want to have kinds of this is number of class plus 1, this is class prediction, and we don't care about this one too much because we're going to run softmax ladder. And for bounding box, we don't change anything here. Okay, so the tiny SSD given input will give you the anchors, all these anchor boxes we have, and the class prediction and the bounding box prediction, three things. Okay, do a little bit of sanity check. It's a little bit complicated here. Well, sorry. So I create a network. The number of classes equal to 1. We initialize it. I fit into the network is batch size equal to 32. RGB channels 3. And the input is 256 times 256. So then given to X, we have number of anchors, number of class predictions, bounding box predictions. So we know the base network gonna divide the width and height by 8. So we get 32. And then we fit into another downsample block, another one, and finally we get average pooling. So this is the feature map size for each scale. And we have 4 anchors for each pixel because we choose 2 sizes and 3 ratios. We get 4 anchors. So in total, we have 4,444 anchors, and in total, we're going to generate. So then you can see that the output shape, the number of anchors, because the anchors are shared across all these batches. So no matter batch size we have, it's always 1, and this is the number of anchors we have. Each anchor box can present by 4 numbers. So this is 4 here. The number of classes, the batch size, and the number of anchors. And this is 2 because we have single class, but plus a background class. We have 2 classes here. Similarly, the bounding box prediction we just concat into 2D shape because of the concating. So which means it's a 4,000 number times 4 give this little bit larger number here. Okay, so you know the shape of this thing. This one. Then also you can see that even it's pretty tiny SSD, we generate a lot of anchor boxes here. It costs a lot of computation overhead. Okay, so now that we have the whole network defined. And next one is like the data reading. We already, in the last lecture, we already talked about, we have the tiny Pikachu data set. Given an image, we put the 3D Pikachus all over around and to get the synthetic data set. So here, we know the Pikachu data set. We choose the batch size equal to 32. And we need to try, we use GPUs and tiny, this is the model we have. We initialize it with XVR, and we choose a learning rate equal to 0.2, and the weight decay is like a small weight decay. Okay, so this is set up. So the other thing is the loss function. Well, we have two kinds of loss here. The first is softmax cross entropy loss. This is for class prediction. So that's normal we have. The other one, the bounding box, we use L1 loss, which is the predicted bounding box minus the ground truth, and use the L1 norm. The reason we don't want to use L2 is because if we do really bad predictions, very, very far away from the bounding box, then we don't want to penalize that too much. So here, then the loss function, we have a lot of things here. This is a class prediction, this is a class label. So the loss function, so we just feed the class prediction and the loss class labels into the class loss here, the softmax loss. The other thing is like the bounding box predictions, the bounding box labels, and here's a mask. We talked about mask before. If there's an anchor box, we didn't find a ground truth bounding box associated with this one, we're gonna mask as 0. So if for this anchor box we find a bounding box associated with this one, we just mask is equal to 1. So here the loss function, we only want to penalize the anchor box predictions actually map to a bounding box here. So if we didn't find any association, which may be a background, then we don't want to penalize the prediction here. But we still need to penalize the loss because we have a background category here. So here, we first get the prediction times the mask to get all these anchors we have, the bounding box, and also the labels times the mask, and do the L1 loss. So this is a prediction loss. Okay, we return, and just for simplicity, we just plus the prediction loss and the class prediction loss plus the bounding box prediction loss. In normal, you maybe have a weight here. You maybe, so here we just, for simplicity, we just adding equally. Okay. So this is the evaluation matrix. So class is easy. We just equals to the number of labels we have. This is the normal accuracy we have. For the bounding box we have here, this is the label we have. This is the prediction. We just minus it. Times the mask. We only care about the bounding box. The anchors have objects. And do just the absolute value and sum together as scalar. This is basically the L1 loss we have. So we call it the bounding box matrix here. Okay. Then we have all of the things. The last one is the training script. A little bit long, but pretty similar to each other. Like, so we initialize something like the accuracy, the minimal, the bounding box, the sum, the bounding box error, and the iterator. We're gonna reset here. So we have the iterator. We have x and y, and the only difference here. So given network, we're gonna 3 output as normal as before, and then given the anchor box, given the anchors we have, and given the labels y, we're gonna do the target. We're gonna map the anchors to bounding boxes. We talked about in the last lecture about that. So then we're gonna return to you the bounding box labels, the mask we have, and those are the labels that we have. Then once the match is done, we feed all the things into to calculate the loss, and so this is a forward function. So in the forward function, given x, you generate the anchors, class predictors, bounding box predictors, anchors maps into the bounding box, generate the labels, and then lastly, you compute the loss. So that's all. So that's what you call a single shot. You get everything together. In the master RCN, you first predict the anchor boxes and then do the prediction here. For here, we just generate at the same time. It's called single shot. Then we have the loss, we do computer gradients and evaluate the accuracy, evaluate the bounding box, and then almost everything's similar, and print the results. So let's see. So the running here is a little bit slow. I can just show the training log we have. Pretty small. Well, let's do. You can see the log here. Well, we only have 2 classes, and that's pretty easy. And the bounding box, you can see that decreases a little bit. Like there's a tiny application here that's pretty easy to train. But again, still like every 5 epoch, even tiny classes take like 20, 30 seconds to run on a GPU. So in general, object detection is much more complex than image classification. The last thing, once we train the network, we want to do predictions. So predictions, given the input X, still we fit into the network. We have the anchor boxes, we have class prediction, bounding box prediction, and we run a softmax on the class predictions to get all these classes we have. The other thing we mentioned that we want to run we have a lot of overlapped anchor box predictions. We just want to remove the duplications. It's called NMS. So then lastly, if it's just the -1, which means we think it's a duplicate, we just remove them, and this returns out the last one we have. So pretty straightforward. So then we read image here and do a resize because the input is like 200 by 56, 200 by 56 as converted floating, and transport to put the RGB channel in the last layer and put the RGB channel into the first dimension, and then prediction here. And finally, we can show that, okay, display that we also talked about that before. Given the thresholding, which is if the threshold means the confident value is larger than the threshold, I'm going to print. If the confidence score is too small, I can ignore to print that out. So what I do here, every time we get a score, if the score is more than the threshold, we're going to continue. Otherwise, you're going to print the bounding box here. So here, finally, you can see that, well, okay, so finally, you can see that given a synthetic image, you got a bunch of Pikachus around, you can see that, well, at least you get all this bounding box right. So the right ones predicted. Usually you can change the thresholding. If you lower the threshold, you get more bounding boxes. You get a high threshold, you get small bounding boxes. So you can see that it's not so confident, 0.37 and 0.54. In the normal way, we pick up is just a 0.5. This is the normal way to choose the thresholding. Okay, so that's kind of all for the object detections. And a little bit more complicated than the image classification, because every time you run a forward, you get a multiple output. And also the output, you want to do a lot of cleanup to show the results. Okay, any questions so far? Question?
Just a very general question. Why did we come up with different numbers for the bounding boxes? Are these, what do they represent? Do they just represent the confidence in detection, and if so, why?
So remember, we have 2 outputs. One's the bounding box, the offset, which is the location. The other one is the class. It is a class prediction. So here, even that we only have a single class Pikachu here, we have another class called background. So this score means I predict this bounded box. I first predict this bounded box, and then I think you have 37% probability you contains a Pikachu, and 63% you just is background. So this is a confidence score. This bounded box contains this object. So this is why you always have, like I can show you the slides at beginning. Like you show this one, you have all these numbers for this. That's a person, 99%. This person is like it's a car. Always you have numbers here. But this one is much more confident. You almost get 99% here. For us, we have tiny SSD. Then we do an ordinary job. Okay, other questions?